My presentation is going to be different than the other ones that have been presented. I don't represent a network operator. I don't represent a solution provider. I am a student of Jeju National University in Korea. So what I present here is a solution that can be done using the MCore platform. So you could see this as a proof of concept. So without further ado, I will start with the network slice selection function of MCore. So these are the contents of the presentation. And I would like to start with this figure. That is a really nice figure. When we speak about 5G, the main motivation for this new technology is not this anymore. We don't worry that much about the smartphones as the drivers for this technology. We see a plethora of services here. We see a lot of services, and most of them, they are not even related to what the smartphone is. So I don't know, guys, if you were present here, like in a few sessions back when SKT made their presentation. They already announced that they have a commercial 5G network implemented, but they don't have smartphones that are 5G. So they are focusing these efforts on trying to cater to these services that exist and that require a good, how can I say, a really like a strong infrastructure for it to work, no? So we have really different services that are like they need applied technology for them to work, of course, no? So thinking about this, is it possible to provide access to these services or cater these services with the current infrastructure that we have? I mean, if we're thinking about physical infrastructure, of course, it's going to be really hard, almost impossible. It's a lot of money, no, that we require to invest. So that's why 5G networks, they have a concept that is called network slicing, no? Network slicing, basically, what it aims to do is by using a single physical infrastructure, single physical channel, provide different virtual channels that will cater to different services. So in this case, I mean, we can see in this picture, there are multiple services, and for them, there exists like a different access networks, but different channels too that will provide the specific functions for the services per se. But what happens now? And it's something too that it's being like solved, especially by the 5G architecture, no? What happens when you have multiple slices? How do you know for which service you're gonna assign a slice to it? So I like this figure of the 5G architecture. There are other ones that has been shown, but this one is cleaner. We don't see that many functions. Most of them, they are recognizable. And we have the network slice selection function here. And it's been proposed by the 3GPP, not just by this current architecture, but before in the LTE networks too. It was there. It was present there. So what is the challenge? Well, the challenge, of course, is that for people that want to have a proof of concept of these network slice selection functions, well, we don't have open source 5G components to work with, especially academia as us. But MCore comes into this as a platform. By default, MCore, it provides virtual network functions and services that can give you end-to-end connection. Sadly, at the moment that we start our research, was at the beginning of the year, there were some problems not related to the EPC problems that Spring just, the licensing problems that Spring just said. There were some licensing problems too with the eNodeB traffic emulator that they had. So for providing like functionality to the network slice selection function, traffic from a user equipment to the data network is crucial. We cannot just work in the EPC itself. Because, as we know, if we have read the 3GPP documentation, the NSSF does the network slice selection on the basis of the user equipment information. So our system overview that we are working on, it's proposed like this. So we have MCore, that practically MCore, I mean, it's compromised by three main services. I mean, we were working in MCore 5.0, now there are more. But these three more components, these three big components that we see here, the EXOS, OpenStack, and ONF. Plus services that will represent the BNF that we are gonna put in the underlying system. So one of the main motivations that we have to use the open-air interface as the EPC and the eNodeB was that licensing problem that we had at the beginning. So by onboarding the eNodeB service, we figured out that, hey, there is the open-air interface EPC, why not use it too? Later, I will give some reference to how this thing was done. It's thanks to the help of some other developers that have been already working in this part for MCORD, I mean the OAI EPC. So basically what we see here is services that are linked to BNF that represent and can communicate with EXOS for having some form of orchestration with them. So this is the key functionality that is required for achieving a network slice selection scenario, the orchestration of virtual network functions. And for that thing, there is a key component that is part of all the core, deployments, that is the synchronizer itself. The synchronizer, it exists for each service that we onboard to the platform. And basically what it does, it just translates, it keeps communication between the state of the BNF themselves and the declarations that we did for building the services and the BNF. So they check, have they changed? Have we instantiated new ones? Have they been deleted, et cetera? And they keep that information and it gives it to EXOS. So this thing is just like how like an end-to-end connection can be done using the open-air interface. It's not that much related to MCORD. I just want to show that it's possible to be done. But basically, any BNF that can run by itself can be put in MCORD, so that thing is not a problem. This thing is basically how the network slice selection function will take messages from the VMME. I don't put the whole messaging sequence. It's really long. I mean, it follows the 3GPP implementation for registration, authentication, and session management. So it's a lot of messaging that is done. I just want to put the basic things. So basically, the user equipment sends a connection message that in that connection message, it includes the IMSI, that International Mobile Subscription Identity, that is confirmed by the MCC, MNC, and IMSN. So that thing is passed to the eNodeB. The eNodeB passes it to the VMME checks with the HSS if the eNodeB is part of the PLMN, and if the user equipment that is connecting to the eNodeB is accessed, et cetera, et cetera. Once everything of that thing is resolved, the VMME will forward this connection message to the NSSF. And the NSSF will have the up-to-date slice information, select the slice, give it back to the MME, and the MME will proceed with the session management. But how? That is the important thing. So this is the implementation that we did for the NSSF. Every BNF that is onboarded on CORD, R-Core, M-Core, any CORD, has a service and has a BNF. The BNF has the actual functionality of the network function. It has the actual code. So in the case, for example, of an EPC service, it has the actual functionality of a BMME or a BHSS or a BEPC. And the service, what it does is just have some declarative options that abstract some of that functionality and brings it up to EXOS to tell them what that network function should do, how it should act if it detects if there is a change in the network, etc. So the main functionality that the NSSF service does is that through the synchronizer that this service has, it will communicate with EXOS to know the current state of the network. So if multiple SPGWs that are going to represent your data plane and multiple SPGWCs that are going to represent your control plane for session establishment are instantiated, the synchronizer will update this information, will send it back to the NSSF service. Through an automation playbook, it will create a script and it will update a database. And this database, it will have the up-to-date slice information. Whenever the network changes again, for example, a network operator creates more BNF, it will update this database again. So the database will always have the up-to-date information. So the NSSF BNF simplifies this by receiving the MME slice request message and just query this database, check that if a slice exists based on the IMSI. We're using the IMSI for user equipment differentiation. For actually, in the end of this presentation, I will show like for the job that we are working on. For service differentiation, right now we are just using the last digit of the IMSI, but in further work, we should be using like something that is called the SNSSI that I will explain later. So this information will be synchronized with the database. We'll check if the user equipment is allowed to use this slice based on the type of service that it's trying to use. Then the slice will be served, and it will come back to the MME. Obviously, this is not as simple as it's put here. Basically, because the MME doesn't know what an NSSF is. I mean, actual functionality of an EPC doesn't consider a network slice selection function. I don't think that the Sprint EPC consider a network slice selection function either. So fortunately, we're working with open source components. So it's easier to change a little bit of the functionality of the MME. So instead of just grabbing a known SPGWC for session management, we'll always ask the NSSF first to check if there is a slice that can serve the user equipment, and we'll take the NSSF slice for selecting the SPGWC that is available. I mean, that has that slice. So it's a communication API that was coded that just translates the request of the BMME into something the NSSF can understand and translate back the NSSF request to the BMME. So basically, the BMME just has a slice database that computes 3 tables. One is a slice table that will be computed in real time. This one associates a user equipment with a slice. In this case, we call like a slice differentiator. And the SPGW table that is filled by the synchronizer that I explained before. This one, the role is that EXOS will be filling this table whenever the network state changes. And the service table, basically what it does, it's a table that the network operator should manage. So they will have different kind of services that, for example, if it's for web, if it's for video, etc. So they will have this information and they will put it in this table. So the messaging that it's exchanged between the MME and the NSSF, it's just the IMSI right now of the user equipment. It's sent directly to the NSSF, and the NSSF will compute, will do the computation in base of that user equipment information. For the scenario that we presented, 2 slices were created. Basically, 2 slices are the instantiation of the BNF itself. I mean, we take literally that network slicing is the instantiation of virtual network functions. So in this case, we have a slice for web, and we have a slice for video. And once these slices are served, a GTP tunnel of the user equipment is created between the user equipment and the SPGWU for the internet. So how can we have a different user equipment? In our case, we are using an open-air interface system emulation because we don't count with a software-defined radio or like a physical eNode B. So everything, we put it inside of MCore, even the eNode B2. So as we can see, this is an EXOS view of all the services that are included in this proof of concept that we have. So the OASIM service, it represents the eNode B and the user equipment. And it's capable of emulating, like, let's say it's 20, but once you emulate more than 3, it starts to struggle. So it's not advisable to emulate more than 3 user equipments. the BMME, the VHSS, SPGWC, and SPGWU are like a standard open air interface, EPC. The NSSF is the service that will represent the BNF of the NSSF that we have created. These are like some instances that can be seen, like it's as part of instances of virtual machines in OpenStack, and they just show what was our topology that we created. The test results, they show like the NSSF. I don't know if you guys have seen how like MCore it's managed. Basically, MCore, you instantiate different kind of BNF, and those BNF, they have their own verbosity, their own way of showing things on console most of the time. So in the case of the NSSF, it's always like, it's a service that is always running. And whenever a BMME request of a slice comes, it will show how many slices are available, how many slices are being served, to which user equipment is being served, etc. If you can see here, this long numeration that we see here is the IMSI. The first, like 1, 2, 3, 4, 5, 6, 7 numbers are always going to be the same because they are working in the same P element. The other ones, they change. I mean, they are specific to the SIM that they are going to be using. So for the case of a slice differentiator, we just check the last digit. But then how do we provide quality of services to these different slides? This thing is something, too, that is native to the open air interface EPC. There is a specific configuration that can be done to the BSPGWU. That in this case, there is a section that is the policy and charging enforcement function, that if we enable it, we can set up some limit for the upload and download, uplink and downlink of the bandwidth. So in this case, I mean, the video slice is limited to 30 megabits per second, and the web slice will limit it 10 megabits per second. That is basically is a standard. In the case, the physical link that goes from the machine that houses the MCore platform is only 100 megabits. So it's not real to put that much because the E0B doesn't handle that much data either. In actual test, the E0B, just by running some iPerf test, it fluctuates a lot. So it cannot show in reality that the slices that have been configured are using the maximum bandwidth for the differentiation of the services. So it's not a reliable way for testing it. But in the case that we test the EPC directly, doing some speed test CLI on the different slices, we can see that, yes, the quality of service policies, they exist. But the E0B is causing a bottleneck for the end-to-end connection. And that thing is something that, well, right now, I mean, we're working with an open source like a component that doesn't have this kind of functionality for a performance test. Maybe if we work with a physical E0B, we can provide we can have the same bandwidth that has in the core network can be replicated in the access network itself. But the important thing is that the selection of the slices is done, regardless if the EPC doesn't have the performance to handle the full bandwidth that the network slices are providing. So if we change the EPC, the NSSF will still be working. So that thing is not the main problem. There is a video. I will not show it here because it will take a long time. But if you guys want to take a picture and look for it, it's a good way for seeing as an example of how this thing runs, how EXOS is managing all these services, and how the different services look when they are running, the BNF when they are running at the same time. And at the end, you can see too, like the different slices that are being created. I mean, how the user equipments are being served by different slices, because the main purpose of this is not creating slices. The next steps that we have in this case, is the migration to Core 6.0, that it changed a lot how the BNFs are managed. Another one is the use of the NSSI, that is the Network Slice Selection Assistant information. And this thing, why it's important? Because it's what 3GPP recommends for doing the slice selection based on the user equipment information. There needs to be like some kind of coding maybe on the E-Node-B, some kind of compilation of this message format that includes two things. One is the service differentiator that will tell, like, I want, for example, web, or I want to use video, or I want the network for IoT messaging. And another one is the slice differentiator that you can have video, but there are lots of qualities of video. You could have a standard video, high definition video, 4K video, etc. So those things give like a further slicing to a network slice. So it's like a different kind of policies that can be coded from the user equipment itself, and it aids for the network slicing scenario. The other one is the easier definition of network services that we're working on it too, and this thing could be a whole presentation for a long time, is the use of contracts for defining the type of services that we're gonna be supporting in a network. Let's think ourselves as a network operator, what type of services we can support, we define the contracts for them. A vocabulary store for storing the network architectures that we can work on. Deploying MCore and deploying new services to MCore is quite cumbersome. It takes a long time, it takes a lot of manual work, it takes a lot of like text files that need to be, even though most of these text files, they are kind of formatted, and there could be templates for them, you need to still fill them manually. So by having a vocabulary store that will hold like templates for these architectures that we are gonna be providing as services, it can make this process easier, as well as a policy configurator that will translate some of the policies that the contracts will put into the underlying system that exists under MCore. So it's important. I know, I mean, it's not a product that can be taken, but I haven't seen like other operators or other people working on core trying to put a different network function that is not the basic EPC, E-Node-B functionality. NSSF is, we consider it really important. It's part of the 5G network. I mean, it's one of the key functionalities of the 5G, it's network slicing. So when you have multiple slices, how will you select them? I guess MCore, it's a solution, not as a commercial use, but as a proof of concept. MCore can give this thing, this functionality to have some synchronization for all the underlying system and give access to a network function for the selection of slices. So the reference that we have here is the 3GPP architecture, the mobile core, and the open air interface. And I want to give a special thanks to Wai Chen, that he's here. His colleagues, they have a lot of good development on the core platform. And they have their own way for managing their own slices and et cetera. So these guys, they have a good demo on the exhibition section. You should hit them and see what they are doing. And of course, my lab mates that they could not come to present here, but they have done a lot of work. So we are almost over time. So if you guys have some questions, I will be really happy to answer them. So, okay, that's it then. Thank you very much.